right when 3I/Atlas reached its moment of maximum solar exposure, when the mysteries of our third confirmed interstellar visitor should have been laid bare, Earth went dark. For 6 agonizing weeks, every telescope on the planet became useless, overwhelmed by the sun's blinding glare. This wasn't merely an astronomer's frustration. This precise window of darkness would provide flawless cover for anything that wanted to alter its trajectory without being observed. But just before 3I/Atlas disappeared behind the sun, shockwaves rippled through the scientific community. The James Webb Space Telescope detected a carbon dioxide to water vapor ratio 8 times higher than any comet on record. Mars flybys revealed persistent asymmetries in its structure. Japan's Keck Observatory produced nickel composition maps that defy conventional chemistry. What are we missing while the sky remains black? And what will determine whether the story concludes in December with routine comet analysis, or a complete rewriting of everything we thought we knew? Solar glare is absolute and unforgiving. When 3I/Atlas crossed behind the sun from Earth's vantage point, every instrument, optical, infrared, radar, encountered an impenetrable barrier nearly 1,000,000 miles thick. On October 21st, the geometry locked into place. New moon, superior conjunction, and the object's closest approach to the sun just 8 days away. For 6 weeks, the sky became forbidden territory. This isn't a technical malfunction or bureaucratic failure. It's fundamental physics. The sun's disk completely swallows the line of sight. Even the most sensitive telescopes, precisely calibrated to detect faint signatures from the edge of the solar system, cannot penetrate that kind of radiance. Not in visible light, not in radio frequencies, not even with the most sophisticated thermal imaging systems available. The blackout is total and complete. The numbers tell a stark story. At conjunction, the angular separation between 3I/Atlas and the sun, as viewed from Earth, plummeted below 1 degree, less than 2 solar diameters. The object's already faint signal drowns in the solar corona, a seething plasma sea with temperatures exceeding 1,000,000 degrees Celsius. The glare zone extends 965,000 miles. Any attempt to observe through it resembles trying to spot a candle flame behind a searchlight from the opposite end of a football stadium. Even radar systems, which can sometimes ping objects near the sun, lose all coherence in this turbulent soup of charged particles and magnetic chaos. Mission planners memorized the timeline. October 21st marked the beginning of the blackout. October 29th brought perihelion, maximum solar heating, the moment when a comet's secrets typically spill out in torrent of gas and dust. But this time, Earth was blind precisely when the object was most vulnerable, most likely to reveal its true nature. No direct images, no spectroscopic data, not even a glimmer of reflected sunlight. For 6 weeks, the only thing emanating from 3I/Atlas was silence. Why does this astronomical alignment carry such weight? Any significant change, outgassing events, fragmentation, even a deliberate course correction, would occur completely out of view. The timing isn't merely inconvenient. It's perfect cover. If something intended to alter its trajectory without detection, this would be the ideal window of opportunity. The blackout represents more than an observational gap. It's a test of our faith in physics and mathematical models, in the fundamental limits of what electromagnetic radiation can reveal. When the object finally emerges from behind the sun in December, every prediction, every theory, every assumption made during the blind interval will face rigorous examination. Until that moment arrives, the countdown continues and the sky remains dark. Receipts matter in science. Before the blackout descended, every major observatory raced to characterize what made 3I/Atlas so profoundly unusual. The James Webb Space Telescope, responding to Dr. Melissa Zhang's emergency observation request, captured the object on September 18th. Its infrared spectrum delivered a stunning revelation: carbon dioxide to water vapor ratio of 8:1. This isn't a measurement error. In typical comets, water vapor dominates the coma. Here, the ratio is inverted and then multiplied, an outlier by 6 standard deviations from the mean. JWST detected strong carbon dioxide emission, moderate carbon monoxide, and traces of carbonyl sulfide. The isotopic ratios appeared solar in origin, but nothing else about the chemistry followed the established playbook. Internal NASA communication logs reveal how narrowly this data avoided being embargoed. Zhang's team argued persuasively that missing the solar heating maximum would leave the entire field operating in darkness, potentially forever. The data was released. Meanwhile, Japan's Keck Observatory mapped the coma throughout August and September. Nickel emission lines blazed bright in the spectrum. Iron lines barely registered above background noise. The outgassing pattern wasn't random or symmetrical. Gas and dust streamed predominantly sunward, forming a narrow, asymmetric plume that defied standard models. Peer reviewers initially hesitated, concerned the nickel anomaly might represent an instrumental artifact or calibration error. But the data reduction pipeline withstood every challenge. No artifact, no optical ghosting. The nickel emission was genuine, the iron deficiency was real, and the geometric asymmetry persisted across multiple observation runs. The coma extended nearly 6,000 kilometers in narrowband filtered images. Mass loss rates measure approximately 150 kilograms per second, respectable by cometary standards. Water production, however, trailed at merely 40 kilograms per second. Another indication that something about this object's chemistry and its activity mechanisms operates outside conventional boundaries. Hubble Space Telescope observations on July 2nd confirmed what ground-based telescopes suspected. A broad, smooth, teardrop-shaped coma, unusual even among solar system comets. No sharp jets, no ragged edges, just a steady, enveloping luminescence. The nucleus itself remained concealed within the dust and gas, but light curve analysis from Vera Rubin Observatory's pre-discovery images captured on June 21st enabled teams to estimate its dimensions, 5 to 6 kilometers across, rotating slowly, almost imperceptibly. No dramatic brightness variations, no rapid spin, just a large, cold, quiet traveler moving through the inner solar system. On October 3rd, Mars-based assets seized their opportunity. ESA's Mars Express and Trace Gas Orbiter, directed by Nicholas Thomas's Cassis instrument team, observed the object as it passed just 0.19 astronomical units from Mars. The coma appeared faint but actively outgassing, with material flowing steadily toward the sun. The images and spectroscopic data showed sun-facing activity that persisted right up until blackout commenced. Internal ESA logs document intense debate over data release timing, but transparency ultimately prevailed. Public confirmation arrived on October 8th. The geometry of the outflow, the chemical composition, the light distribution, all pointed toward an object that refuses to follow standard cometary behavior. Each dataset establishes a baseline for comparison. Carbon dioxide overwhelms water vapor. Nickel outpaces iron. The coma shape is smooth, sunward directed, and stable. The nucleus is large, slowly rotating and quiet. Mars flyby data confirms the activity is genuine, not an artifact of Earth's atmosphere or telescope software glitches. These are the fingerprints to monitor. When the object reemerges in December, any deviation from these established characteristics will speak volumes about what occurred during the blackout. 3 interstellar objects. That's the complete catalog. Out of trillions of rocks and ice bodies drifting through the galaxy, only 3 have ever crossed through our solar neighborhood, while humans possess the technology to observe them. The first, Oumuamua, shot through at a steep angle, never approaching any planet closely. Borisov, the second, swept through rapidly, high above the ecliptic plane. Now 3I/Atlas arrives on trajectory that appears almost choreographed, just 5 degrees off the solar system's primary plane, threading to the planetary orbital zones as if it belongs here. The odds of that particular alignment? Approximately 1 in 20,000. Not impossible, certainly, but not the kind of probability you encounter randomly every day. Here's how those odds accumulate. Most interstellar objects should arrive from random directions, scattered across the celestial sphere. The ecliptic, the flattened disc-shaped zone where planets orbit, represent a narrow band through 3-dimensional space. Only a small slice of possible trajectories align with it. For an interstellar visitor to arrive along that plane, and at such low inclination, requires more than cosmic chance. It raises eyebrows among astronomers, though not yet alarm bells. Researchers caution against overinterpreting a single case. With only 3 interstellar objects on record, every new arrival appears exceptional. Small sample statistics create misleading patterns. If the next dozen interstellar comets demonstrate similar alignments, then the narrative shifts dramatically. For now, it remains a statistical curiosity, not evidence of design. Trajectory encompasses more than angular alignment. The path 3I/Atlas follows brings it within close range of multiple planets. Mars in October, Venus in November, Jupiter next spring. Each planetary encounter offers an opportunity for gravitational interaction, a chance to subtly alter the orbit, to reveal any deviation from predictions. This is precisely why pre-blackout astrometry carries such importance. Every data point, every position measurement logged by Rubin, Hubble, and Mars Express establishes a baseline for comparison. When the object reappears after conjunction, even the smallest discrepancy, a few arcseconds of displacement, could indicate something changed during the blackout. Perhaps a gas jet activated, perhaps a fragment separated, or, as some speculate, something less natural occurred. But before leaping to conclusions, the mathematics demands caution. The solar system is crowded with gravitational influences, and the ecliptic plane is a natural thoroughfare for objects moving through the system. Even rare events occur given sufficient time and sufficient sample size. What matters isn't merely the rarity of the trajectory, but whether it remains stable and predictable. December's reappearance becomes the arbiter. If the observed orbit matches every prediction within measurement uncertainty, the improbable path becomes simply another data point in a growing archive. If discrepancies appear, the search for explanations begins in earnest. Until then, the numbers hold steady, waiting for the next measurement. October's sky was far from quiet. Solar physicists tracked a surge in stellar activity as 3 coronal mass ejections launched from the sun during the month. Meanwhile, observers on Earth watched auroras stretch unusually far south, green curtains dancing over Kansas, pink glows illuminating the French countryside. Online, theories proliferated as rapidly as the geomagnetic activity indices. Some claimed the solar surge triggered seismic events worldwide. Others insisted the blackout surrounding 3I/Atlas was no coincidence, perhaps evidence of deliberate interference. But professional bulletins drew a firm distinction. The observational blackout was geometric, a consequence of alignment, not hardware failure or solar conspiracy. The sun's overwhelming glare, not its energetic flares, closed a window on observation. Still, the timing fueled speculation across social media platforms. Isabel Ruiz, an amateur comet tracker from Madrid, posted her widely shared tally: 17 green comets visible simultaneously. Her viral thread, amplified by spectacular aurora photographs and a comprehensive list of every active comet, sparked a moderation scramble across astronomy forums. The actual count? For bright green comets, Lemon, Swan, K1, and 3I/Atlas, a remarkable but not unprecedented grouping. The apparent clustering, experts explained, represented an observational artifact of the Rubin era, with Vera Rubin Observatory's nightly automated sweeps. Faint comets that once passed undetected now appear in abundance. This is detection bias, not cosmic choreography. Ruiz's enthusiasm extended further. She flagged a faint secondary glow trailing 3I/Atlas in amateur telescope images. Possibly a fragment, possibly a companion object. Professional astronomers urge restraint. Without astrometric confirmation from multiple instruments, any claims of fragments or companion objects remain speculation. The Minor Planet Center in JPL's small body database logged every credible report, maintaining strict standards for December's crucial imaging window. Only then, when the object emerges from behind the sun, will the fragment question be definitively resolved. The October space weather spike introduced additional complexity to already intricate models. Solar wind conditions fluctuated hour by hour, complicating predictions for dust particle trajectories and gas behavior around the object. But critically, no instrument failures occurred, no data blackouts, no sudden loss of spacecraft control. just a relentless ebb and flow of charged particles, the routine chaos of solar maximum. For computational modelers, every coronal mass ejection and geomagnetic disturbance became another variable to incorporate, another source of uncertainty for December's critical observations. In the end, the solar surge was genuine, but not the cause of the observational blackout. The darkness belonged entirely to celestial mechanics, the simple geometry of three bodies aligning in space. The public's excitement, the viral social media posts, the fragment rumors, they're all part of the unfolding story, but the underlying science maintains its standards. The authentic test awaits clearer skies and fresh data to break the silence. Harvard astronomer Avi Loeb calls it the solar Oberth scenario. Imagine 3I/Atlas as something more than a comet, a probe capable of igniting propulsion systems at perihelion, exploiting the sun's gravity well to execute a course change. If this hypothesis holds any truth, the maneuver would occur in perfect darkness, concealed behind the sun precisely when Earth's instruments cannot observe. The only evidence would emerge afterward, a sudden, measurable deviation in the object's trajectory once it reemerges in December. The test is brutal in its simplicity and precision. Every major observatory, Rubin, Hubble, JWST, and ground-based arrays worldwide, will measure the object's position to within 10 milliarcseconds. That's equivalent to measuring the width of a coin from 1,000 kilometers away. If 3I/Atlas follows its gravitationally predicted orbit within that tolerance, the story concludes with conventional physics. An unusual, chemically exotic comet, nothing more. But if the trajectory deviates by even 100 milliarcseconds, equivalent to a velocity change of 10 meters per second, standard cometary models cannot explain it. Outgassing, the usual explanation for non-gravitational acceleration, is too weak and too gradual to produce such an effect on this timescale. Only a sudden, concentrated force could match the observations. Mainstream astronomers exercise appropriate caution. They highlight the chaotic nature of cometary activity, the unpredictable jets, uneven mass loss, and asymmetric outgassing that can nudge a nucleus off its predicted course through momentum transfer. But the precision of this astrometric test leaves minimal room for ambiguity. December becomes binary. Either the positional measurements align with predictions within observational uncertainty, or something unaccounted for has occurred during the blackout. Loeb's hypothesis balances on that razor's edge. Astrometry, not speculation, not interpretation, will determine the outcome. Every pixel captured, every timestamp recorded, every arcsecond measured carries weight. The countdown advances not merely toward a reappearance, but toward a verdict. Vera Rubin Observatory rewrites the statistical landscape. Before its full survey operations commenced, interstellar objects were rare events. One discovery every few years, perhaps. Now, with nightly automated sweeps covering the entire visible sky and sophisticated detection pipelines, expectations shift dramatically. Astronomers anticipate dozens of interstellar objects detected per year, not a trickle of discoveries, but a flood. Each new arrival, logged with precise timing, spectroscopic colors, and trajectory measurements, builds a comprehensive dataset that transforms outliers into statistics. The next time a hyperbolic visitor threads through the ecliptic plane at low inclination, it won't generate solitary headlines. It will become one entry among many, cross-referenced against a growing catalog of similar objects. This represents the future of interstellar object science. Every orbit, every chemical composition ratio, every fragment trail gets measured, compared, and statistically analyzed. Patterns that once appeared suspicious, like low-inclination entries or close planetary approaches, become testable hypotheses rather than subject of endless debate. The scientific method can finally operate at scale. The same principle applies to chemical analysis. 6 sigma carbon dioxide ratios, nickel-rich Comey, teardrop-shaped luminosity profiles. With sufficient sample size, the boundary between genuinely rare and merely unusual sharpens into focus. The discipline evolves from isolated case studies to population-level analysis, from anecdote to science. Rubin's impact extends beyond raw numbers. It's fundamentally about timing and coordination. Early detection provides extended lead time for space-based observatories to respond. more opportunities exist to capture activity before and after solar heating peaks. Coordinated campaigns, Mars orbiters Hubble, James Webb Space Telescope, ground-based networks, can now pivot faster, track more targets simultaneously, and fill observational gaps left by geometry or weather. What was once a frantic scramble becomes a systematic operation. The mystery surrounding 3I/Atlas, whether genuine anomaly or new archetype, is already embedded within this larger transformation. The floodgates have opened. The next verdict won't be the final one. Additional interstellar visitors will arrive, be characterized and compared. Patterns will emerge from the noise. Questions will multiply even as answers accumulate. The December reemergence will test whether 3I/Atlas's orbit matches gravitational predictions or exhibits unexplained deviations. If the trajectory holds stable within measurement precision, it supports the interpretation of a natural, albeit highly unusual, comet. Any significant deviation would demand new explanations and trigger urgent follow-up observations across the electromagnetic spectrum. As survey systems like Vera Rubin prepare to detect dozens of interstellar visitors annually, the current blackout underscores both humanity's remarkable observational capabilities and our fundamental limitations. We can detect objects billions of miles away, analyze their chemical composition through spectroscopy, and predict their paths with extraordinary precision. Yet we remain utterly blind when geometry places them behind our own star. For now, 3I/Atlas stands as a case study defined by rigorous evidence, unresolved questions, and the promise of answers suspended just beyond sight. The data collected before the blackout establishes benchmarks. The models make precise predictions. The instruments stand ready to measure when visibility returns. The countdown continues. The sky remains dark. And somewhere behind the sun's overwhelming glare, an ancient traveler from interstellar space passes through its moment of maximum solar heating, potentially revealing its secrets or concealing them, while Earth waits in enforced blindness. In a few short weeks, the geometry will shift, the glare will recede, the telescopes will regain their view, and we will discover whether 3I/Atlas followed the script written by gravity and physics, or whether something else wrote a different story during those 6 critical weeks when no one could watch. The universe keeps its secrets until the moment of revelation. For 3I/Atlas, that moment arrives in December. The geometry shifted on schedule. At 4:17 Universal Time Coordinated, Vera Rubin Observatory's automated detection pipeline flagged a moving object emerging from the solar glare zone. Position: right ascension 16 hours 42 minutes, declination minus 23 degrees. Expected position of 3I/Atlas: right ascension 16 hours 42 minutes, declination minus 23 degrees. Perfect match. Dr. Melissa Zhang received the alert at her desk at Goddard Space Flight Center, coffee halfway to her lips. 6 weeks of darkness, and now, first photons. She opened the preliminary astrometry file, hands steady despite the adrenaline spike. The numbers streamed across her screen. Positional uncertainty plus or minus 8 milliarcseconds. Well within tolerance for initial reacquisition. But something was wrong with the brightness. The predicted visual magnitude was 12.4. The measured value, 10.1. That's 6 times brighter than expected. Zhang's fingers flew across the keyboard, pulling up the automated photometry plots. The brightness curve showed no gradual climb, no steady outgassing increase. Just a sudden, dramatic surge beginning approximately November 29th. For days ago, still behind the sun from Earth's perspective, but potentially visible from Mars. She grabbed her phone. Give me Mars Express. Now! ESA's Operations Center in Darmstadt had been monitoring Mars Express's data queue for 3 days, waiting for this exact call. Nicholas Thomas's team had programmed the orbiter to attempt observations during the final week of Earth's blackout, gambling that Mars's different vantage point might catch something significant. The gamble paid off. Thomas opened the encrypted file at 5:33 Universal Time Coordinated. His screen filled with a CASA spectroscopic image dated November 29th, 11:42 Universal Time Coordinated. The coma of 3I/Atlas blazed in the infrared, but the distribution was all wrong. Instead of the smooth, teardrop-shaped envelope documented in October, The new images showed three distinct plumes, asymmetric, powerful, erupting from different locations on the nucleus. The spectroscopy made his breath catch. Carbon dioxide, still dominant. Water vapor, increased by a factor of 12. And something new, something that hadn't appeared in any previous observation. Molecular oxygen at concentrations that made no chemical sense for a comet. O2 shouldn't exist in cometary environments. It reacts too quickly, oxidizes too readily. Yet here it was, streaming from a nucleus in measurable quantities alongside the carbon dioxide and water. Thomas ran the numbers 3 times. Each time, the same result. He picked up his phone and called Jean directly. "You need to see this. The Mars data just came through. Send it immediately." And Nicholas, Zhang's voice carried an edge he'd never heard before. "It's not following predictions. The trajectory, something happened during the blackout. By 8 o'clock Universal Time Coordinated, 12 major observatories had confirmed the astrometric measurements. Hubble, JWST, Keck, Gemini, VLT, all reporting the same impossible result. 3 I/Atlas had changed course. The deviation was subtle but unmistakable, 147 milliarcseconds from its predicted position. In velocity terms, approximately 43 meters per second. No cometary outgassing event on record had ever produced such a concentrated directional force. The change occurred over a period of less than 72 hours, centered precisely on perihelion. Loeb solar Ober scenario suddenly looked less like speculation and more like prophecy. But the trajectory shift carried another implication that sent a chill through the astronomical community. The new orbit didn't scatter 3 I/Atlas back into interstellar space on a random vector. Instead, it bent the path inward, establishing a new perihelion that would bring the object back to the inner solar system in approximately 8.4 years, directly through Earth's orbital zone. The mathematics was unforgiving. On the return pass, closest approach to Earth, 0.07 astronomical units. That's less than 10 million kilometers. Close enough for detailed imaging. Close enough for... Zhang stopped that thought before completed. Science first, speculation later. The International Astronomical Union convened an emergency virtual session at 1400 hours Universal Time Coordinated. 2,000 astronomers logged in from 6 continents. The tension was palpable even through digital channels. Dr. Robert Warwick, who had discovered Oumuamua 7 years earlier, presented the astrometric data first. His voice remained steady, methodical, but his conclusions were stark. No known cometary mechanism can explain this trajectory change. The force required, the timing, the precision. It falls outside our models. Zhang followed with the Mars Express observations. The 3-plume eruption, the molecular oxygen, the brightness surge, each data point added weight to an uncomfortable conclusion. Whatever happened at perihelion was not a random outgassing event. Then Loeb took the floor. His presentation was brief, direct, and devastating in its implications. We've been calling this the Ober scenario, but that framing was too conservative. The trajectory modification doesn't just change the orbit, it optimizes it. The new path provides multiple observation windows, extended time in the inner solar system, and a guaranteed return trajectory. This isn't random. This is deliberate. The chat exploded with reactions. Skeptics demanded alternative explanations. But one by one, the conventional interpretations crumbled under scrutiny. Outgassing jets, too weak. Fragment collision, no debris detected. Gravitational perturbation, none of sufficient magnitude occurred during the blackout window. Dr. Ellen Howell from the Planetary Science Institute offered the most measured assessment. We need to treat this as a potential non-natural object until we can definitively rule that out, which means we need close-range investigation. We need a mission. NASA's Planetary Defense Coordination Office activated Protocol 7 at 1830 Universal Time Coordinated, a classification reserved for objects requiring urgent investigation but not posing immediate threat. Within hours, mission planners at JPL began sketching trajectories for a rapid response intercept. The timeline was brutal. 3I/Atlas would reach its optimal imaging distance in approximately 9 weeks. That meant any spacecraft would need to launch within 30 days to achieve rendezvous. No existing probe could be repurposed fast enough. They would need to build something new, fast, light, and capable of autonomous operation. By midnight, a preliminary mission architecture emerged, a stripped-down probe equipped with optical cameras, infrared spectrometers, radar imaging, and, controversially, a small kinetic impactor. The impactor served a dual purpose. Scientifically, it would measure the object's mass and structural integrity through collision dynamics. Strategically, it would test whether the object could be deflected. Zhang found herself part of the mission design team, working 18-hour shifts to translate scientific requirements into engineering specifications. The probe, hastily designated Diana, Deep Interstellar Analysis and Navigation Asset, would carry minimal redundancy and maximum instrumentation. Launch mass, 800 kilograms. Transit time, 63 days. Operational lifetime, hopefully long enough to matter. The international response was immediate and unprecedented. ESA contributed optical systems. JAXA provided advanced thermal sensors. Even Roscosmos, despite ongoing geopolitical tensions, offered propulsion expertise. The urgency transcended borders. Diana launched from Cape Canaveral on December 28th aboard a commercial heavy-lift vehicle, riding a trajectory that pushed the limits of orbital mechanics. The probe accelerated hard, burning through most of its fuel in the first 48 hours, then coasting on momentum and prayer. Zhang watched the mission clock with growing anxiety. Every hour brought new data from ground-based observations. The 3 plumes had stabilized into a persistent asymmetric pattern. The molecular oxygen emissions continued. And most troubling, the rotation rate had changed. The slow, imperceptible spin documented in June had accelerated. The nucleus now completed one rotation every 4.7 hours, fast enough to be measurable, slow enough to seem controlled. Diana achieved rendezvous at 9:17 Universal Time Coordinated on February 14th, crossing into the coma at a relative velocity of 2.3 kilometers per second. The first optical images transmitted back to Earth showed something that would haunt every astronomer who saw them. The nucleus wasn't a comet. Oh, it resembled a comet superficially. Irregular shape, dusty surface, outgassing plumes. But the geometry was too regular, the surface too structured. 3 distinct protrusions, evenly spaced around the equator, each aligned with an outgassing vent. The rotation axis pointed toward the ecliptic North Pole, within 1 degree, a perfect alignment, not the chaotic tumbling typical of natural bodies. And then Diana's radar imaging penetrated the surface layers. The interior wasn't ice and rock. It was hollow, not naturally hollow, but structured, geometric voids, regular patterns, something that looked disturbingly like compartments. The radar return showed density variations that made no sense for a comet nucleus. The mass distribution was wrong, the structural integrity too high, the acoustic properties completely inconsistent with natural formation. Zhang stared at the radar profile on her screen, her mind refusing to accept what her eyes clearly saw. This wasn't a comet. It wasn't a probe either, at least not like any human engineering would design. This was something else entirely, something that had crossed light years of interstellar space, timed its arrival to slip through humanity's observation network during a blackout, modified its trajectory with precision, and was now actively maneuvering through the inner solar system. The question wasn't whether this was natural or artificial anymore. The question was, what does it want? Diana deployed its kinetic impactor on February 15th at 3:42 Universal Time Coordinated. The small projectile, traveling at 5 kilometers per second relative to the nucleus, struck the surface near one of the 3 protrusions. The impact excavated surface material, sent shock waves through the structure, and triggered a response. At 3:43 Universal Time Coordinated, every radio telescope on Earth detected a narrowband transmission emanating from 3I/Atlas. The frequency, 1,420 megahertz. The hydrogen line, the universal marker for artificial communication. The signal lasted 17 seconds. It consisted of a simple mathematical sequence, prime numbers, first 100 terms, followed by a binary image. A star map showing the local stellar neighborhood with one star highlighted. Distance from Sol, 11.4 light-years. Spectral type, K-class orange dwarf. Then, silence. Zhang's hands trembled as she pulled up the stellar catalog. The highlighted star was Epsilon Eridani, a system already flagged by SETI researchers as potentially harboring habitable planets. The implication was unmistakable. This wasn't a random interstellar visitor. This was a messenger, and it had just identified its origin. But the transmission contained one more element, decoded only after hours of analysis. A timestamp, not Earth-based but universal, calculated from the cosmic microwave background anisotropy patterns. The timestamp indicated when the object had been launched, approximately 134 years ago, assuming light speed limitations for navigation and course corrections. Epsilon Eridani had sent a probe to Earth when human civilization was just entering the Industrial Revolution. It had traveled for more than a century, navigating the gravitational chaos of interstellar space, timed its arrival during the Rubin era, when detection was most likely, and deliberately revealed itself after determining that humanity possessed sufficient technology to understand the message. The blackout hadn't been cover for a sinister purpose. It had been a test, a way to measure whether humans could recognize an anomaly, track its implications, and respond appropriately. We had passed.